Okay, welcome back, everybody. I hope you had a restful break. Don't think it was long enough for any of us probably, but we're back here. We're gonna circle back. So some orientation for what we're doing today. So we're gonna finish up the last couple of slides in the regulation of ventilation packet, which was where we kind of left off right before break with ventilation perfusion ratios. And then we're gonna segue into our renal stuff by thinking about another thing that both your ventilation and your kidneys can regulate. So we're going to go into acid-base balance as our next topic, as our kind of segue into the renal system. Okay. So we're going to kick off, and I'll let you know when that's happening. So where we left off, we were talking about ventilation perfusion ratios. So we learned about the fact that we're trying to match how much air we're getting into our airways with how much blood is flowing past them. Okay, so we talked about what those different parts of the ratio mean. So to get us back up to speed, you can look at the picture for this. Let's remember what it means if we have a ventilation perfusion ratio of less than 1. Click us through kind of quick so we get to our kidney stuff. Okay, so for our reminder, perfect. Yeah, so our ventilation perfusion ratio is really just dividing the amount of ventilation or the rate of ventilation by our perfusion, which is our blood flow. So the way we would end up with a mismatch equaling less than 1 would be if we don't have enough air. So decreasing that top value, decreasing that ventilation rate is going to pop you below 1. That's a problem. You'd get above 1 if you have the blockage in your blood flow, creating a drop in the perfusion part of our ratio. Okay, so pulling through that. Okay, so if we have a blockage in our pulmonary capillaries, so in the blood flow, what's that going to do to our partial pressures of our gases? You should be able to see this on that picture too. Look. Okay, so what's going to happen here if you block the capillaries, so if you block the blood flow, what that's going to result in, you might have been thinking in different places relating to the blockage. But if you're thinking about the blood that's kind of in contact with the alveolus, it's going to be getting enough oxygen, right? So it's going to get lots of oxygen in it, but it's not going to be getting rid of its CO2. Okay. So basically what we're thinking about, the reason we're thinking about these ventilation perfusion ratios is we have those partial pressures of the gases of the carbon dioxide and the oxygen having effects on how big our bronchioles are, so how big our airways are essentially, versus how big our arterioles are, so the capillaries, the pulmonary capillaries, that blood flow past our alveoli. And mainly we have our carbon dioxide acting on the bronchioles, so carbon dioxide acting on the airways here, and oxygen acting on the arterioles. So acting on that blood flow piece. And our goal is to bring that ventilation perfusion ratio back to 1, right? Even if we have a little blockage, a little constriction somewhere going on, be it in the bronchiole or in the blood flow. Okay. So I am going to point out, as you're looking at this stuff, what's happening in the pulmonary arterioles is different than what happened when we were talking about what happens in our arterioles out in our body generally, right? We were talking about the smooth muscle in arterioles in your systemic circulation as being mainly responsive to high CO2 levels. So this is different here, right? So our pulmonary capillaries respond differently. But basically, we're going to try to get back to matching up our ventilation with our perfusion. Okay. So if we have a drop in ventilation, so if you stop breathing so much, say you have some constriction in your airway, you're increasing resistance, or you're literally choking, you block something off, something like that, or you breathe in a particulate, right? What's going to happen in the air first, you're going to end up with building up carbon dioxide in the base of that alveolus, right? As the blood is still bringing carbon dioxide in, right? It's doing gas exchange in the base of the alveolus, but that air isn't getting out of your mouth, okay? And we're going to see a drop in the O2 in that alveolus, right? Because we're not breathing as much new fresh air in. The blood is going to come to equilibrium with those values. Your body doesn't like this. We want to keep our partial pressures matched. So we're going to react. Okay, so we have this increased carbon dioxide in the alveolus, right? And that's going to trigger the bronchioles to try to dilate, right? We're going to try to get rid of that carbon dioxide. We know too much carbon dioxide is a problem. So we're going to expand our airways. That's our bronchodilation piece. The oxygen is going to be mainly triggering the effect in the arterioles. So the pulmonary arterioles passing into the pulmonary capillaries going by those alveoli. So they're going to sense that lower oxygen, right? And what they're going to do is constrict. And that piece is about trying to get that ventilation perfusion ratio back to 1, back to normal. So we do the opposite for perfusion. Okay? So if the perfusion is our problem, so if we have a blockage, a blood clot somewhere in the arteries going to our lungs, right, that's going to drop down our perfusion of the pulmonary capillaries. Right? So the result there is going to be an increase in our partial pressure of oxygen because we're still breathing in enough air, but we're not carrying enough carbon dioxide away. Okay? So this is the opposite problem to that ventilation problem above. And we're going to have the opposite effect. Okay? So we're going to see that increased oxygen levels in the arterioles. So we're talking about arterioles first this time because we're really thinking about an arterial problem if we have a decrease in perfusion. Okay, so the first thing we're going to try to do here is we're going to try to vasodilate. And then on the bronchial side, we're going to try to bronchoconstrict to pull that ventilation down to match the blood flow to that, hopefully just a section of your lung rather than the whole lung, really. Okay. So that's the big gist here. So we can walk through it step by step, but basically you want to know that ventilation and perfusion should be matched. We're trying to make them equal. If we have a drop in one of those because we have a blockage in either an airway or a blood vessel, you're going to see changes to correct that, to try and bring them back to equal. We don't want to bring extra blood to an alveolus that can't do gas exchange anyway. We want to try to bring air around blockages, that kind of stuff. Yep. So our triggers for this are our gases. So in this example, we're looking at a situation where we have an increase in carbon dioxide and a decrease in oxygen levels that we're noticing in the alveoli and in the interstitial fluid around them. So that fluid between the tissues that's going to be neighboring our blood. Okay, so we're going to look at those effects on the bronchioles first. So that's our airways. So what this is going to do in this local regulation here, This is going to decrease our contractile activity of the smooth muscle, right? So we're not going to clench so hard in the smooth muscle surrounding the bronchioles, which expands them. That's bronchodilation. This is going to lower the resistance of our respiratory tract as a whole. Right now we've got big wide tubes, easy to breathe in, easy to move air. AKA we're increasing our ventilation here. And now we can go to the opposite side. So on the arterial side, on the blood flow side, the effect of this increase in carbon dioxide and drop in oxygen, particularly the drop in oxygen, is going to be to increase contractile activity of the smooth muscle. So that's an opposite effect to what's going on in the bronchioles. You're going to have the cells are different. They react differently to these stimuli. So they're going to squeeze harder, which means they're constricting. So vasoconstriction, because vaso is for our blood vessels. This increases the overall resistance of the pulmonary circuit, which means we're going to drop down our perfusion, drop down blood flow here, hopefully somewhere along this by increasing our ventilation and decreasing the perfusion. We're going to bring our ratio back to 1. Okay. That's basically all we want to know about that. We're trying to get to 1. We're going to dilate or constrict airways and blood vessels till we get there so that we're not putting blood somewhere it doesn't need to be or bringing air into places where we can't do gas exchange anyway. Okay. All right, so we're going to move on to our acid-base homeostasis. And we're going to be linking together here our respiratory system and our urinary system. So we are going to be referencing some of that kidney stuff that you hopefully watched and remember. So we're going to be segueing into our renal system here. But we're starting here because this is where your lungs and your kidneys are working together to control something that's really important in your blood, right? So we're controlling our pH because we're controlling the balance of acids and bases in your blood, which is really important. If this acid-base balance goes haywire, your whole body is kind of going to shut down. Okay. A reminder about pH. So our pH scale goes from 0 to 14. Okay. We're going to have parts of this that are going to be regulated by the respiratory system. And particularly, that's going to be carbon dioxide, right? That makes sense. Breathing is going to help us control our carbon dioxide levels because we're breathing out carbon dioxide as we breathe in oxygen on the reverse side. Since we haven't gone through the renal system as a whole yet, we don't know much about that side, but I'm going to tell you that the renal system is going to play into this largely by affecting our concentration of bicarbonate ions that are going to act as a buffer for carbon dioxide in the blood. And we'll talk about what that means and why that's important in a second. Okay. But because we're trying to balance these two things, carbon dioxide and bicarbonate, we work together to control the pH. And even a tiny change in pH is going to have a huge, or potentially huge, physiological effect because your cells are in this environment all the time. This is what's influencing the aqueous environment that they're bathed in, right? Like all the fluid surrounding the cell is going to be at approximately these pHs as well. And this is going to influence how proteins act that are embedded in cell membranes, which means we're affecting receptors. We're going to affect the behavior of neurons. We're going to affect all sorts of things if we change the environment that cell is in. So our normal pH that we want is between 7.35 and 7.45. Okay. So technically the H in the pH is for hydrogen ions or protons. Okay, so we'll get to that in a second. But just note that that's on there. So normal, about 7.35 to 7.45. Okay. Now, if we drop below this, the low end of the pH scale is where our acids are, right? So anything below 7.35, we're going to refer to as acidosis, so too much acid, right? Which if you were just thinking about hydrogen ions, not the carbon dioxide, yes, yet that would be too many hydrogen ions, okay, if we were using our typical kind of chemistry way of thinking about pH. For our opposite side, right, at the higher ends, we have our bases. So if we get above 7.45, we're going to refer to that as alkalosis. So that really means that we don't have enough acid, right? We're becoming too basic, we're becoming alkaline on the opposite side. Okay. Now, if you get too out of balance, this is fatal, and it's fatal fast, right? Just a couple of seconds, if you get above 8 or below 6.8, are going to be fatal. Hopefully, we're never going to get to that range because we have both our lungs and our kidneys working hard to protect us. Okay. And the reason these are fatal, right, is because when we change pH, we change hydrogen ions, right? We're changing all those charges. We know proteins fold, right? And they're folding based on their R groups, of which we have many options, of which we have many types, but they're interacting with each other, right? So if you change the charges around them, they're going to fold differently because they're going to interact differently with those charges. When we have a protein that's misshapen, it can't do its job, whether it's a receptor for something, whether it's a channel, whether it's a transporter, whether it's an enzyme. We have problems if our proteins are misshapen. In general, the kind of symptoms you would observe as you get kind of out of whack on the acidosis end, so the too acidic end, the low pH end, is you're going to be depressing the central nervous system, right? So we're going to see not enough firing of our nerves and our neurons in our brain. And on the opposite side with alkalosis, you're going to see a hyperactive central nervous system. So everything's going to be firing all the time, which includes misfiring, right? Which is also a problem. Okay. So how does this relate to lungs or to kidneys, right? So we're going to have a couple of different kind of chemical relationships that we're going to think about to understand how these systems are all working together. So one thing, we know there's hemoglobin in the blood, right? We've thought about the fact that our hemoglobin is carrying oxygen around. We also know that the hemoglobin is interacting with carbon dioxide as well. It's not binding it directly to those heme groups, but we do have some minimal binding of carbon dioxide to hemoglobin. Okay. Now, hemoglobin is also interacting with hydrogen ions, with those protons. Okay. So hemoglobin can either bind them or release them. So it's going to act as a buffer in your body. So buffers, remember, we're thinking like a sponge, right? So it can soak up some of our extra hydrogen ions, and it can release hydrogen ions. You can squeeze out those extra hydrogen ions. Okay. So what this would look like, so HB is our hemoglobin, right? So here you see our oxygenated hemoglobin here could be separated into oxygen, hemoglobin, and hydrogen ion. And we can also combine our hemoglobin with hydrogen ions. Now, it happens to be the case that deoxygenated hemoglobin, so deoxyhemoglobin, is a greater affinity for hydrogen ions. So if you don't have oxygen bound to that hemoglobin, it's going to soak up hydrogen ions easier. But hemoglobin isn't really the main buffer we're going to be interested in this unit. What we're really going to be thinking about mainly is bicarbonate. So bicarbonate is also acting as a buffer. Okay. So here's a bicarbonate ion. That's that HCO3 minus. Okay. So here's our bicarbonate ion. Okay. Our bicarbonate ion combining with that hydrogen ion, with that proton, going to give us our carbonic acid. So we've seen this before, kind of in the reverse, right? So carbonic acid, we know, is also convertible into carbon dioxide and water. And each of these reactions can go either way, right? So you can start with carbon dioxide and water, combine them to make carbonic acid, and then dissociate them into bicarbonate ions and hydrogen ions, or it can run the reverse way, right? So what's happening here when we write it out this way, right? We've seen a bicarbonate ion has soaked up some hydrogen, giving us this carbonic acid, right? But we can also view this the opposite direction, right? So we can see this carbon dioxide level turning into carbonic acid may then release bicarbonate and hydrogen ions, okay? And that opposite direction is why we think of carbon dioxide as a respiratory acid. You can think of those hydrogen ions that carbon dioxide releases when we run this direction, when we run here from right to left, as having kind of like more of an effect on the pH than that kind of weak buffer bicarbonate. Our desired ratio, or our normal ratio here between our carbonic acid and bicarbonate is going to be about 1 to 20. And you can see here, death on either side of that little range of acidosis and alkalosis next to our normal range. Okay. So here's our technical equation for how we would calculate pH. I'm not going to make you calculate pH, but we want to be able to think about this ratio, because that ratio that we see within the Henderson-Hasselbalch equation is what we're going to be trying to regulate. Okay. So if we want to keep the pH of our blood at around 7.4, right? We've got a range of 7.35 to 7.45. So around 7.4. Our ratio here of, now we're going to think about it as bicarbonate ions and carbon dioxide. It's going to be 20 bicarbonate ions for every little carbon dioxide molecule, right? So bicarbonate acts as a buffer, but carbon dioxide has a big effect every time we get more carbon dioxide. Okay. So if we were trying to keep this in balance, and we're trying to keep this 20 to 1, this means that when we have a disturbance, you can act on either side of that relationship. Just like in our ventilation perfusion ratios, you can affect the ventilation part, you can affect the perfusion part. Now that we're thinking about acid-base balance, right, we can affect how much bicarbonate we have, or we can affect how much carbon dioxide we have as we're trying to keep things in balance. Okay. So it's the respiratory system's job to regulate carbon dioxide. Right? You're breathing in and out, you're ventilating in order to make sure that you're breathing off enough carbon dioxide. Usually we're thinking about breathing off because this carbon dioxide buildup is such a problem. Okay. Your kidneys, most of the renal unit will be thinking about how they're regulating really water and some salts, but the kidneys in this acid-base balance are responsible for the bicarbonate side of the equation, right? So your kidneys are going to be able to put bicarbonate ions into your bloodstream or take them out, essentially. Now, when we talk about the kidneys in this context, when we talk about them regulating the bicarbonate ions, we're going to refer to this as metabolic regulation. Okay. And we'll come back to that as we start to piece this together. Okay. So when we have acidosis or alkalosis, that means we might have a problem with our breathing, or we might have a problem with the kidneys, right? Because they have to work together to control the carbon dioxide levels and the bicarbonate levels. I guess that one goes on top. Okay. So we're going to think about the respiratory side here first. Okay. So our respiratory system is controlling carbon dioxide by controlling our breathing. Okay. So for that part, when you're in respiratory acidosis, what our problem is here is we have increased levels in the blood of carbon dioxide. It's a respiratory acidosis, really means that you're not breathing fast enough to get rid of all the carbon dioxide in your bloodstream. On the opposite side, respiratory alkalosis means that we don't have enough carbon dioxide, right? We think about too much carbon dioxide being a problem, but too low is also a problem. So respiratory alkalosis, you want to think about the fact that when we breathe out, right, we're breathing out carbon dioxide every time. So you can't breathe too fast. You can drop that carbon dioxide level down too far. So putting that together with what we just saw in the Henderson-Hasselbalch equation, as well as what you saw about some of the direction words related to our kidneys are going to answer this question. I'm going to draw a little review about what some of these words mean as you do this. Okay. So when we're thinking about kidneys, right, if we have a respiratory problem that's putting us out of balance for our pH in our blood, we're going to try to fix it with the kidneys, right? If it's a breathing problem, we're going to try to fix it with the kidneys. If it's a kidney problem, we're going to try to fix it with our breathing. So what we're going to be talking about as we talk about our kidneys is a structure called the nephron. In our nephrons, we have blood go into a network of capillaries called the glomerulus. The blood continues surrounding the nephron, going through peritubular capillaries. Okay, so that's our blood. Our nephron looks like a little Pac-Man surrounding the glomerulus. All right, so this is our renal corpuscle and our Bowman's capsule here. And we'll talk about all that jazz at length as we go through the kidneys. Okay. And we go into the rest of the nephron, starting with our proximal tubule here. Okay. So this is enough to draw on our direction words. So for our direction words here, I'm going to add on all of them. Okay. So we're going to think about filtration is when we have our first bit of fluid and other stuff going from blood, so from this glomerulus, from these capillaries, into the nephron. So that's filtration. So I'll just put an F. Filtration is that way. If we have that fluid continue out of your body and you pee it out, that's excretion. I'm just going to put an E here. Okay. And then we have these other two words, reabsorption and secretion. So these are modifications kind of along the course of the nephron in the pathway. So reabsorption is what happens if we have this fluid, we filtered it out of the blood, filtration, and then we reabsorb into the bloodstream. So that's our reabsorption. And secretion is going to be when we have stuff that we make and we put it into this fluid in the nephron that eventually is going to get excreted. Okay. So those are four kind of direction words here. Okay. So this in mind, we're thinking about those bicarbonate ions, right? We're in a situation of respiratory acidosis. How can we fix that? With our kidney, with these processes of filtration, reabsorption, secretion, or excretion. Take a look. Okay, great. Okay, yeah. So what we see here. Okay. Right. So what we've done in this situation, right? We're trying to keep our ratio of carbon dioxide to bicarbonate steady, right? And we want our ratio of 20 to 1. Okay. So acidosis, we're in respiratory acidosis. This means we're too acidic. Carbon dioxide is our acid here in this ratio. So respiratory acidosis means our carbon dioxide level went up, okay? Too much carbon dioxide in the blood. Okay. To keep us at this 20 to 1 ratio, we can increase our bicarbonate buffer, right? So we can shoot that up too, right? This is something that your kidneys could maybe hopefully do for you. Okay. So if we want more bicarbonate in the blood, right, what we're going to have to do is we're going to have to take bicarbonate from somewhere in the nephron. We'll get to exactly where that is as we walk through the kidney side of this. We're going to have to take it from the nephron, and we're going to have to put it into these peritubular capillaries. So these capillaries that have already filtered some fluid into the nephron. We're going to pull some bicarbonate back into the bloodstream, reabsorb it. Now it's in the blood, so it can balance out that carbon dioxide. Okay. This is all about balance. And that is why we need to think about the kidney side as well. So this pulls us into our renal unit. Okay. So our kidneys, just like our lungs, want our arterial blood to have its normal pH. We got a little wiggle room on the either side of 7.4. So we've got our normal range, 7.35 to 7.45. Too low a pH, and you're in acidosis. Too high a pH, you're in alkalosis. Okay. We know, and your kidneys know, this causes problems because it messes up your proteins, and proteins do practically everything in your body, right? Hemoglobin is a protein. Voltage-gated sodium channels are proteins. Carbonic anhydrase is a protein. We have tons of enzymes involved in metabolism. They're all proteins, right? Proteins are making your body work. Okay. So mentioned that in particular, part of why this is a death level problem is the effect on the central nervous system, which is your brain and spinal cord. Okay. So if you're in acidosis, you depress the central nervous system to the point that your brain can't function, can't make you breathe, can't make your heart beat, can't do any of the things it should be doing. Alkalosis, these neurons get too excitable. Think firing too wildly. Think, this is not the part that's going to kill you, but think like seizures are too much firing too, right? Too much firing is also a problem. Okay. So we will talk in the future about the fact that your kidneys are also balancing other things. So they're going to be balancing, in particular, sodium and potassium. So when we get there, we're going to see that acidosis, so too much acid in your blood, too low a pH, tends to be associated with too much potassium as well. So hyperkalemia. Look at that K in the middle. K is for potassium, right? So potassium ions are K plus. Okay. So too many potassium ions tends to be a problem that goes along with acidosis. Too few, hypokalemia, goes with alkalosis. Okay. So we'll talk about potassium balance kind of at the end. Other things that are going to be happening alongside this, right? You're going to be thinking cardiac arrhythmias, you're going to be thinking about your blood vessels behaving inappropriately because we have nerves going to them as well. Particular vasodilation tends to happen, right? Lots of stuff is happening. So big picture, we know carbon dioxide and bicarbonate are important for maintaining this balance. We do also, especially when we're thinking about the kidneys, want to think about the fact that there are other things that affect the pH of your blood, particularly the H part, right? The hydrogen ions themselves, for which pH is named. So you have things that put hydrogen ions into your blood and things that pull hydrogen ions out of your blood. Yep. So things that would be putting them in would be things you're eating, as well as metabolic processes going on in your body. So as you're breaking down proteins and fats, you're going to be putting some hydrogen ions into the blood. Carbon dioxide, it's partially getting converted into hydrogen ions. You have lactic acid, you have keto acids, potentially also building up that acidity of the blood as you do metabolism, as you make ATP. Ways we can remove acid from the blood. If we want to actually remove hydrogen ions from the blood, you're going to have to pee them out. So the hydrogen ions themselves are going to get into your urinary system, into your kidneys. That is one of the ways that we're going to be able to fully remove hydrogen ions, not just buffer them out with bicarbonate. Or because carbon dioxide kind of turns into hydrogen ions in the blood, removing carbon dioxide, the gas, will also have the effect of dropping down those levels of hydrogen ions in the blood. Okay. So again, here is that relationship between carbon dioxide and hydrogen ions, right? So this is what we just saw from the section that's from your respiration chapter, except in the reverse, right? So carbon dioxide can be combined with water using an enzyme, carbonic anhydrase, to create our carbonic acid, which can be split into bicarbonate and hydrogen ions. And we now know that we want a ratio of 20 bicarbonate to 1 carbon dioxide, right? So when you turn carbon dioxide into a hydrogen ion and just 1 bicarbonate ion, the net effect that you're going to see is that increase in acidity in that hydrogen ion. Okay. So normally, our partial pressure of carbon dioxide in your arteries should be at 40 millimeters of mercury, right? So in your systemic arteries, you're pumping blood, partial pressure of 40 for carbon dioxide, passes by your tissue, pulls excess carbon dioxide, that byproduct of metabolism, into it, goes up to 46 in the veins, goes back to your heart, then gets pumped to your lungs, where hopefully you're breathing out that extra carbon dioxide that you picked up from the tissue, setting you back to 40 to go around again. Yep. So we talked right before break about chemoreceptors that are helping us regulate that, right? So we have receptors that sense O2 levels and carbon dioxide, but mainly carbon dioxide levels, that adjust our breathing when we see carbon dioxide out of whack. And now we know also that our ventilation perfusion ratio is being regulated as well. Okay. So when we think about carbon dioxide, right, the place that is really coming into your body, right, is not the carbon dioxide that you breathe in. There's a minuscule amount in the air around you, right? But the carbon dioxide that's in your bloodstream is really because you like ate glucose in some form, right? Or you ate something else as a carbon-based molecule. It's like all of them, right? Like mainly we think about carbohydrates when we think about metabolism, but we know that we break down proteins and fats too. They're all carbon-based molecules, right? So when we do metabolism, we're peeling off those carbons as we run towards our electron transport chain, and oxidative phosphorylation to make ATP. So the carbon dioxide is coming from the fact that you're breaking down molecules for energy, and we have this as a byproduct, and it gets into our bloodstream. So that's why we think of our source of carbon dioxide as being from your metabolism. The way we get rid of that carbon dioxide is through the respiratory system. So when we breathe out our excess carbon dioxide. So our respiratory system regulating that carbon dioxide can put us into either acidosis or alkalosis if it's behaving inappropriately. When we have an increase in carbon dioxide, that's our respiratory acidosis. We didn't breathe enough of it off. When we see drops in carbon dioxide, this means that we're in respiratory alkalosis. It means that we're managing to breathe off too much of it too quickly. Now, kidneys can also be a problem, right? So it's not just carbon dioxide that can throw our body out of whack, that can throw the pH into our undesirable ranges, right? So metabolic acidosis has to do with either literally gaining too many protons, too many hydrogen ions, or losing too many bicarbonate ions, because our bicarbonate ions are supposed to be buffering out the carbon dioxide. Okay. So really, any problem creating a pH disturbance that is not carbon dioxide, we're going to refer to as metabolic. Okay. We're saying acidosis, metabolic acidosis. In particular, we're saying something has decreased your pH, so moved you down below 7.35. So this might be that you're eating a particularly high protein or high fat diet, which is producing a lot of those protons, those hydrogen ions, because of the different way that we break down those molecules for energy. It might be heavy exercise. So think like building up lactic acid in your body, right? You're adding acid here. Or you might have a problem with the bicarbonate part. Particularly, the most common way to see that problem, to see too little bicarbonate, would be like severe diarrhea. Creates, in particular, a loss of bicarbonate ions because your body kind of doesn't have enough time to suck them back into the blood. And in general, renal dysfunction, so kidney damage or disease, can mess up all of this, but particularly bicarbonate as well, depending on what the disease is and what the problem is. Alkalosis could be the opposite. So metabolic alkalosis, we're still thinking any problem affecting the pH, putting us above 7.45, that doesn't have to do with our CO2 levels. Okay. Now, common way for this to happen would be vomiting a lot. You have lots of hydrochloric acid in your stomach, right? That's what your stomach acid mainly is. So if you vomit a ton, you are actually expelling lots of acid from your body, right? If you expel acid, you're going to swing yourself towards that basic alkaline side. Might be the case that you've eaten too much of something really alkaline. So if you swallowed a ton of baking soda, this would put you into metabolic alkalosis as well, because baking soda basically is bicarbonate. Or again, renal dysfunction, so kidney disease can mess up your pH balance in all sorts of ways. So that could also be the problem here. Okay. Regardless of the cause, when we see an acid-base disturbance, so when we see our pH outside of that 7.35 to 7.45 range, we're going to try to get it back to where it should be. And we got kind of an order of steps for this. So our first line of defense is going to be just buffering out any changes in the acidity. So buffers, basically sponges for chemicals, right? So we can soak up hydrogen ions, or we can squeeze them out, put them back into the bloodstream. Okay. So buffering of hydrogen ions with hemoglobin, or in particular with bicarbonate, is going to be able to limit changes in pH because we're soaking up excess, or if we have too little, we're going to see a release in some of these. Now, this doesn't like reverse the actual problem. This doesn't reverse whatever is putting the pH into our undesirable range. We could add more buffer to buffer more stuff out, but we haven't fixed the problem exactly with this. Okay. If we want to fix our problem of our disturbance of acids and bases in the blood, we move to our next step. So the next easiest thing to do, other than to just buffer out that pH, is going to be to change your breathing, right? You can do that consciously. We do that reflexively, subconsciously as well, right? So we can change our respiration, change our breathing in order to reverse changes in pH, because we will be changing our carbon dioxide levels, which are one of the main things affecting pH in the first place. So this is a homeostatic regulatory mechanism. Your body is really invested in this. We are regulating that pH very carefully. Okay. So you can start by trying to change your breathing to get back to our desired range. Or if that's not working, if the problem was your lungs, what the problem was your breathing, you're not likely going to be able to fix it with the lungs. So that's when we move to our third step. So our third step, our third line of defense, is our kidneys. So renal compensation can also really reverse changes in pH, because it can actually change the concentration of things in your blood. We're not just kind of soaking it up, but still having that stored for later in our sponge, our buffer. Right? So in renal compensation for our acidosis or alkalosis, we are going to see that we can change hydrogen ions and bicarbonate, basically. So if we have too many hydrogen ions, right? So hydrogen ions are acids, right? That's what creates an acidic pH. So too many hydrogen ions, we're talking about acidosis here. Right? Our kidneys are going to be able to secrete hydrogen ions, right? So our secretion direction. Here's a nephron. We'll get very familiar with them. Right. It's not a great one, but this is the out of your body direction. That's our excretion. Filtration is going in here. When we say secretion, we're moving into our nephron from blood that's bypassing it, right? So if we secrete hydrogen ions, you're ultimately going to pee them out, right? So that can fix it. Or we can reabsorb more buffer, or even make new buffer. So reabsorbing would pull more buffer into the bloodstream. And we can also do the reverse, right? We can shut down that secretion of hydrogen ions, or we can shut down reabsorption of bicarbonate, as we choose. Right. I'll pick up here next time.